Okay, here in lecture 16, we're going to take a look at something called exception handling, which is the C++ mechanism that tries and almost succeeds in dealing with the problem of errors discovered while programs are executing. So you call a function, and the code in this function is executing, and along the way it discovers some kind of error. You've got a divide by zero problem, you've got a bad subscript problem, you're trying to allocate memory that's not available, you try to access a file that doesn't exist. What is this function supposed to do now that it's discovered this error? Well, in traditional languages that don't provide something like exception handling, there are about 5 different techniques that are used. Maybe the most common one is to return some kind of error value. For example, if you have a set of int and you do a find of, let's say, 27 in the set, if that 27 is not found, that is, the find member function fails, we know that find returns the .end iterator for the set, which is a special value indicating an error, that is, indicating that we could not find the value. Another approach that's much less common is to require the user to pass in a pointer to some kind of error parameter or a reference to some kind of error parameter that the function will fill in with some value if it discovers some error. Yet another approach is to use a global variable. This is actually done by some older library routines, and set that global variable to some kind of error value if the function fails for some reason. Now, of these three, returning an error value often works, but it can't always be used. For example, if you're computing the log of some value, that log function is returning some approximation of a real number, and any real number is a valid log of some value. So returning some kind of special error value in that case just doesn't make sense. Math functions like log, exponent, sine, cosine, square root are so commonly used that it would be unreasonable to expect a programmer to provide an additional error parameter that they had to check every single time they called a math function. Assigning a value to a global variable is not a great idea because programmers frequently forget to look at the value of the global variable after they call a function. Or for that matter, they forget to set the global variable to a clear state before they call a function. So another couple of, quote, techniques, unquote, are you can display an error message and just keep limping along until some catastrophic problem occurs, or you can simply give up and crash or exit from the program. So all of these techniques are used. None of them is particularly wonderful. And the general problem with all of these approaches is that the calling function, or the calling object, is at the conceptual level in the program where we can make a decision about what to do if something goes wrong, but the called function is the function that discovers that something is wrong. So we have this mismatch between where we have some idea what we would like to do about a problem and where it is that we detect that a problem exists. And this is why in C++ and other languages, the notion of exceptions was introduced, so that if a function detects an error, the function can do what's called throwing an exception back to whatever called the error detecting function. And then the caller of the error detecting function can catch, if it wishes, these thrown exceptions and can in some way handle the error that occurred. We already know about 2 kinds of errors that will crash our program. One is if we attempt to ask for a chunk of memory and that attempt can't be granted. For example, here we have an array of 1,000 pointers to long doubles, and we're going through each of the elements in that array and storing into that element the address of a new long double array of 1 billion elements. Well, a single long double is 16 bytes, so here we're allocating 16 gigabytes with every use of new, and for sure that's going to fail, very likely the first time through the loop. Another situation where we know our program is going to crash is if we have a vector or a dec in which we're able to do subscripting using an integer index between 0 and 1 minus the size of the container. When we use the at member function and give an index that's outside the bounds of the container, we know that will throw an exception and that will crash the program. Okay, so these are two different kinds of the so-called standard exceptions. If you attempt to allocate memory with new and new cannot get you the memory that you've asked for, new will throw what's called a bad alloc, that is a bad memory allocation exception. On the other hand, the at member function in a container, if you access an element that's outside the range of subscripts for that vector or dec, that throws what's called an out-of-range exception. It turns out that these standard exceptions are organized into a hierarchy. Standard exceptions are actually classes, and throwing an exception involves creating and throwing an object of a particular exception class. These standard exceptions have as their basemost class a class named exception. All right, so a bad alloc is a kind of exception. An out of range is a kind of exception. It would be awfully handy if all of these standard exceptions were described in the same header, but unfortunately the headers for these different kinds of exceptions tend to be sort of scattered around. Bad alloc is described in the new header. Out of range is described in the standard except header. And exception itself is described in the exception header. So let's take a look at how we could use this in actual code. Here on slide 5, we have what's called a try block, meaning that we're going to try to execute a sequence of statements. We have a suspicion that one or more of those statements might fail and throw an exception. So following the try block, we have a series of catch clauses. Okay. So a try block consists literally of the word try and then an open curly brace followed by a sequence of statements followed by a closing curly brace. And what that means is we are going to try to execute these statements. We are hoping that these statements will all succeed, but it's possible that one of them will fail and throw an exception. So if an exception gets thrown by something within the try block, we have a sequence of catch blocks set up, and this is organized from most derived to least derived kind of exception in much the same way that we did with dynamic casts. We had CEO at the top, then manager, then employee. So here, bad alloc is one kind of exception that we might catch if new fails within that try block, or out of range is an exception that we might catch if we use the .at member function to access an element that's not within range in a vector or a dec, and there are various other things that might throw out of ranges as well. Now, if the exception was not bad alloc and was not out of range, then if it is a standard exception, it will be caught by this third catch block where we're looking for just plain old exception. And then finally, if the exception that occurred was not even a standard kind of exception, as your very last catch block, you can use the 3 dot symbol. And if you use the 3 dots, that should always be the very last catch in your sequence of catch clauses associated with a particular try block. Now, notice in the try block that if a particular identifiable kind of exception occurs, and if that exception is a bad alloc, then we will get a reference to the particular bad alloc object in this parameter named E, and we can access the internals of E to try to figure out exactly what went wrong. Likewise, if an out of range occurred, the out of range exception will be available to us through this reference E, and we can try to figure out why the out of range occurred, and so forth.